This was the end of our discussion on Friday, but before I come back to this, I wanted to point out two things. The chapter I just gave back to you, we talked quite a bit about confidence intervals, and the acceptance or rejection of a null hypothesis is our confidence interval containing the number we want to look at, which most of the time is 0. Is our average equal to 10 or not? Are we confident that the average we got is close enough to 10 to be within the confidence interval? If it isn't, then reject the idea that the average is really 10. So in the confidence interval discussion, there were no null hypotheses, which made it very weird for me to see on some papers, we're going to reject the null hypothesis here. What hypothesis? There wasn't one. So while these are two sides of the same coin, they are distinctly different in their application. The other thing I saw frequently was, should we be using t-scores or z-scores? And it comes down to whether we know the population standard deviation or not, or are we told specifically to use a normal distribution? Even if we're told to use a normal distribution, we have to then look at our sample size. Is our sample size big enough? If it's too small, then I need to adjust and use the t-distribution. There's different standards in different books. Our book says use 30 most of the time. Yet one of the problems in our homework said 30, said they knew that the process had a standard deviation of 3.1, and then used a t in the back of the book. Now, mind you to say, I flipped the table at that point. And so if you did it with a z, I gave it to you. Because to me, they said, here's the population standard deviation. The process is known to have a standard deviation. Has nothing to do with the sample I took. That's the population. But they didn't say it explicitly. So using t instead of z in places where it is warranted is going to be a judgment call. I hope that wasn't a phone ring. So, in addition to finding, in this case, that our result was within our confidence interval, that we do not reject our null hypothesis because our critical value was 1.96, and the z we came up with is much smaller than that. And for a two-tail test, we need it to be bigger than in absolute value. I can say, there's a difference between statistical significance and practical importance. All right, wait a minute. Statistically significant means I was able to reject my null hypothesis. I was able to come up with some relationship here, some data that said, no, that's not what we expected it to be. Use the alternative hypothesis, throw this sucker out. Practical significance. A legitimate question, because it's been debated now for almost 80 years. Does smoking increase the risk of cancer? Does anybody in this room think that smoking is good for you? The number that the original Surgeon General's report put out was that there is a 20% increase in the likelihood of getting cancer if you smoked. A 20% increase. Why, in my lifetime, were there millions of dollars of lawsuits over this idea? If it's this big an increase. Because in the actual medical study, the chance went from 0.0001 to 0.00012. That is a 20% increase. The chance went from 10 in 100,000 to 12 in 100,000. The cigarette company said, no, that's bullshit. That's statistical error. That's within the margin of error. You shouldn't reject the null hypothesis because that's not far enough away. They lost those lawsuits, and that's why the tobacco companies are no longer sponsoring events. That's why it's not the Winston Cup in racing anymore, because the Winston-Salem Tobacco Company can't do that. They're not allowed to sponsor the cars. But if I tell you I can guarantee you a way to increase the battery life on your phone, will you do what I tell you? I'm going to increase it by 2.5 minutes. Is it worth it? Statistical significance versus practical importance. If I'm going to increase it by 2.5 hours, maybe 2.5 minutes. Somewhere in there is a worthwhile discussion on whether or not our statistically significant event is worth it. That discussion happens outside of the math of the class. That happens with a value judgment. That happens with all of your other liberal arts classes where you decide what means something and what doesn't. Remember our mercury in the light bulbs contamination question? Remember, we went from 3.5 milligrams to 3.59 milligrams. All right, somebody tell me the percentage increase here. What's the percentage increase in the amount of mercury in this light bulb? 2.5%. The EPA finds this company in violation of their advertising standards for a 2.5% increase. Statistically significant? Yes. Practically significant? I don't know. How bad is mercury poisoning in the area? How much mercury goes downstream from these disposed bulbs into the water supply, into the fish, where it accumulates, and then we eat them? Okay, no, I'm just going to give up fish. That's not a great reaction to this news, is it? But that's a legitimate question. Is this just a statistically important piece of information, or is this practically important? Mercury contamination was a very big deal in the last 15 years. I'm going to say the same exact comment about carbon dioxide. And you all are going to go and have a giant global warming discussion somewhere else. because I'm not going to have that in this class. But then I can ask, if the increase is 0.01% additional CO2 put into the atmosphere, is that statistically important or practically important? And the only way to make that decision is to not just take the numbers, take the rest of the impact in the rest of the world into account. And that is why, in spite of the fact that you're going into business or science or law or whatever you're going to do with your life, it's the whole reason you take a stats class, so other people can't bullshit you with numbers. One of the biggest pieces you will see is someone will attempt to conflate the two or deny the connection between the two. Things that are statistically significant may or may not be practically important. And things that are practically important may or may not be statistically significant. But that's a value judgment, not a mathematical one. Questions? Cost-benefit analysis, price-earnings ratios, profit margins, all of those things go into practical importance concerns. The one that stands out to me is the Pinto. Anybody know the car, the Ford Pinto? Why is the Ford Pinto famous? No, that wasn't a Ford Pinto. That was an AMC Gremlin. It would blow up. The fuel tank was placed between the back rail and the back axle. If that car got rear-ended, it stood a very good chance of breaking open the gas tank and exploding. Ralph Nader made his career suing over the Ford Pinto. Ford ran a cost-benefit analysis. Are we better off recalling all the cars and replacing the gas tanks, or paying out the lawsuits for the people who died? Guess which was cheaper? There was never a recall on the Ford Pinto. A value judgment, not a math judgment. So I want you all to remember that in your business decision-making strategies, while we're learning all of the statistics, it's one piece of a very large pie. Questions? The testing for averages that we did involved a known population standard deviation. What if I don't know the population deviation or the population variance? Because those are connected ideas. I'm still trying to figure out whether or not my average is within my confidence interval or not. What did I say right at the beginning of class today about the difference between those two universes? Where I know the standard deviation of the population and where I don't. Seriously, it hasn't even been 15 minutes yet. What did I say was the difference between where I know the standard deviation of the population and where I don't? T versus Z. That's exactly it. T versus Z. So I'm going to do exactly the same thing here, but I'm going to build a T rather than a Z. Everything else gets decided in the same way. Instead of having a Z calculated, I will have a T calculated. And that means instead of using sigma, I use S, the standard deviation from my sample, rather than the standard deviation from the population. And instead of using the normal distribution to get my T critical, I'll have to use the student T tables to get my T critical. Everything else we do for testing whether or not our mean is in our confidence interval or not is the same. We just switch out Z for T and sigma for S. But wait a minute, in order to use the T distribution, what other piece of information do I need to know? My degrees of freedom. And how do I get degrees of freedom? Bingo. So everything else in the process can be the same. Problem number 37. The manufacturer at Glowmore flat white interior latex paint claims one coat coverage of 400 square feet per gallon on interior walls. This is how much paint you need to cover 400 square feet. That's 1 gallon. A painter buys 6 gallons and finds coverages as follows. So this guy paints his way through 6 gallons of paint. And he says, with one coat, I covered 390 square, 360, 410, 380, 390, 360, 400. Now, which is more important? That we be equal to 400, greater than or equal to 400, or less than or equal to 400? If I say on the jar of paint, on the gallon can, will cover 400. Aha! If I'm doing that, then I want a one-tail test. My hypothesis should be, oh, coverage is bigger than or equal to 400. Well, if that's what I'm guessing at, then that'll be my null hypothesis. And that means my alternate is, what's my alternate hypothesis? Say again? Exactly. So, what I need is to know whether I'm doing a left, right, or two tail idea here. Where do we reject? Do we reject when we are left? Do we reject when we are right? Or do we reject when either is true? I reject to the left. That makes this a one-tail, left-tail test. Okay. I need a calculated t-value and then a critical t-value. The critical t-value, I don't actually need to do any calculations for, because that comes right off of the student t-table. Appendix D. What are my degrees of freedom? Say it again. 5. There are 6 data values. N is 6. Take one away. I have 5. So I'm actually going to write that down here. DF 6 minus 1 is 5. So I go to the 5 table. DF 5. Now, what confidence interval? It says in the problem at the 10% significance. So alpha is 0.1. That's our 10 level of significance, which is a 90% confidence interval. But alpha itself is the significance for a one-tail test. Notice that the significance lines in the table are given both for a 1 and a 2. One-tail test, 10. I go down to DF equals 5, 1.476. Since I'm doing this to the left, I should use the negative value, because this picture shows the right tail, yes? Therefore, I want the left, I'm going to use the negative value. Flip the picture over. Great. By the way, you can do that in Excel because the t-tables are in there. I do t inverse of 0.1 with 5 degrees of freedom. That's the Excel command to generate this same number. What do I need to do the calculated version? And more. I need the standard deviation and the mean, which means I have to generate those. You are welcome to put this data into Excel and ask it for the mean and the standard deviation. I'm going to use the data format here on my calculator. I'm going to put all of the numbers into a list. And then I'm going to ask it to do the descriptive statistics for one variable. And there we are, mean, standard deviation. It gave me 2 standard deviations. It gave me an S and a sigma. Why? I'm using S because I don't, the sigma assumes this is the whole population and thus divides by something bigger. Divides by n instead of n minus 1. We're using a sample. I'm going to use S. I will go ahead and keep 2 decimal places here for the standard deviation. So I'll call that 20.66. And then for the mean, I'll do 383.3. But those are numbers we have to work out. We have to calculate ourselves. Now, What is the calculated t-value? Same calculation. The average we got minus the thing we think is the average over standard deviation over the square root of n. We use our standard error. Somebody give me a number. At least 2 decimal places. 1.976. Negative. Do I see a bunch of nodding or a bunch of disagreement? Talk to me, people. Okay, I got a couple of agreements. If this isn't what you got, walk me through your calculation. Close enough. 1.98 if you want to use it to 2 decimal places. I'm good with that. Okay. Questions on actually getting the numbers? Yes, sir.
What's the
That's my critical value. That's the one that tells me 10% of the area is below that number. So this number right here negative 1.476 tells me that this area is 0.10.
what's this negative 1 point?
So here's my question. Is the number we calculated in that region or in this region? If it's in the shaded region, do I accept the null or do I reject the null? That's too far down for me to be confident that the average should be where I want it. So the 1.976 being in here means I should reject my null hypothesis.
What does that represent? What's that the t-value of?
I'm not sure how to answer that question at first. The t-value itself, the one I calculated, tells me how far down I have to go to get an area where this would be right. And that is smaller than my cutoff value. If it's beyond this number, you've gone too far. I don't have faith in the average being 400. I think that tells me that I'm wrong, that the average really isn't 400. So I reject the null hypothesis. Wait a minute, that means that the thing that is correct is my alternate hypothesis. So I believe that the advertising for this paint company is false. I now have reason to doubt their advertisement. Your can says it'll cover 400 square feet, but but I don't get an average of 400 square feet. I get less than that. And I got so much less by comparison to the standard error that I think you've told me a lie. Now, this may also tell me that I need to do more than 6 walls. Maybe I shouldn't just deal with 6 gallons. Maybe I should be dealing with 30 or 40 or 50 gallons, right? Maybe if I'd taken a bigger sample, I'd get a different answer. But I don't know. What it tells me is that this evidence is not enough to support their claim. This evidence does not support them. And that's what this number tells me. It tells me what it would need to be for me to support them. Didn't get close enough. But I could also ask, how significant is the answer I got? So I've drawn that little orange marker there, right? To the left of the 1.496. So what if I only shaded in the stuff that was to the left of this number? How much area would that be? So grab your t-distribution. Now our t-distribution is problematic in that it only gives me certain t-values, right? I can't use it the same way I use the z. Oh, crap. I need a better table to be able to look up what the right thing is for the area that we actually calculated. I want to know what that little bitty right-hand area is. Now, problem. What I really should be doing at this point is calculus. No, not just no. Hell no, I'm not doing calculus in here. So, open up Excel for me. Grab your calculators and look at the distributions. What I need is to find the t distribution for negative 1.98 with 5 degrees of freedom. If you're in Excel, you can type this command in exactly like this. Huh?
So saying you entered too few arguments.
Mine says X.
Yeah, okay. Take off the 5, put in a 1. Does Phil say too few?
So it's 15.
No, just make it 1. All right, hang on a second. We're going to do this the hard way. I'm going to open Excel right here.
This
Right?
parentheses X, comma, degree freedom, comma, Q.
Okay, so we need them both. So I need comma 5, comma 1. I made a copy error in my notes. So degrees of freedom is the 5. The 1 is the cumulative distribution function. I want you to tell me the total area under that. That's why I use a 1 there. If I used a 0, it would just give me the height at that one spot. That's not helpful. That's not an area. So I want to use the cumulative, which tells me 1. What'd you get?
4, 5, 2, 3, 11.
Okay, and if I do that on here, I go to the distributions, and I say, oh, I want the t that's cumulative. And I can say, give me negative 1.98 as a number, 5 degrees of freedom. Same number, yes? Is this bigger than or smaller than my level of significance? What's my level of significance? That's alpha. That's 0.1. This is smaller than that, right? If it's smaller, too unlikely to have happened by chance. Now, please notice. Yes, ma'am.
Can you do that on the calculator?
Absolutely. So under distributions, distributions are here above the variables button. Second, distribution. I want a t value. There are a bunch of t's right here, yes? The inverse t, that's how we get the number for the critical one, right? For the calculated one, t inverse. Here, that's the PDF, that's just giving me a height. CDFs give me area. It says go all the way from the left up to negative 1.98 because we're doing a left tail. Yes? So that 1E99, that's negative infinity as far as this calculator is concerned. Go up to 1.98, and then I put in my 5 degrees of freedom. I hit enter here. It writes out the command. And then when I hit enter, it does the calculus. Or at least it approximates it. Because there are functions for the PDFs and the CDFs. I just didn't make you memorize them because they suck. $64,000 question. Does it matter? This is statistically significant. We rejected a null hypothesis. Is it practically important? Have any of you had a summer job painting walls? House painting? I see those things outside all the time. How many walls do you do in a summer? So if you had to buy an extra gallon of paint because you came up short one day, that money would come out of your pocket, right? Maybe, since my average was 383, I'm 17 square feet short every gallon. My average was much lower than 400. If I'm only painting 2 or 3 walls, I don't care all that much. But if I'm painting a company's worth, if I was painting this building, next time they renovate this building, change the colors again, like it's green downstairs, right? Okay. How much paint do we have to buy? A lot. So that becomes the question of practical significance, depending on what you're doing. If I'm painting the interior of my house, I don't have that much painted wall space. I'm good. If I'm painting the interior of a commercial building, I might be very pissed off to come up short on the coverage. On the other hand, we chose a significance of 0.1. The book gave me that, pulled it out of thin air and just handed it to me. What if I had picked a significance of 0.05? Now, there are two different ways to answer this question. One of them is to go do another T critical, which is what it looks like you were doing, Matt. What'd you come up with?
2.015.
But I'd use the negative, right?
Right.
But our calculated value was 1.976. Would I have rejected my null hypothesis? No. If I'd say you have to be 95% sure that this is too small, you'd say I can't make that call. The other way to do it doesn't require me to look up another t value, because I would get the same p regardless of what my significance level was. And then this 0.0523 is bigger than 0.05. I don't reject. I'm not sure we're far enough outside because I need to be smaller than 0.05. And you came in at 0.0523. It's really close, isn't it? So your significance, your choice of significance level matters a lot. How do you decide what the significance level should be? Are you willing to make more type 2 errors or more type 1 errors? Are you willing to let something false go by, or are you willing to reject something true? That's another value decision. Question?
Well, so like if we did it for 0.01, we would know that it would pass as well.
Yeah. As soon as we know this 0.0523, I know that any significance smaller than this will pass. I'll say, all right, you're still within what I considered the margin of error, because I'm only off by 5.23%. That's a wrong way to put it. I don't want to say it that way. It's not by I'm off by that much. It's that that's the likelihood that this happened by randomness. By the way, what if instead of doing 0.1 as a one tail, I'd done 0.1 as a two tail? That would change my hypothesis, wouldn't it? My hypothesis, instead of being greater than or equal to, would just be equal to. But then again, I would have passed. Because when I go to the two-tail test, that's the same as 0.5 on the one-tail test. So I get a different number. Why? Because it's two tails, so half of that 10 is down here and half of that 10 is up here. And that's why the 0.10 on the two-tail is 0.05 on one tail. I wrote down a note that says example 5 on page 334 also does this very well. Example 5 on page 334. Talks about temperature in hot chocolate. People, I don't care how hot your hot chocolate is, but I used to. Although it wasn't exactly chocolate at Bruegger's Bagels, it was hot coffee at McDonald's. Anybody know that story? Ben, you're nodding, tell me. the coffee temperature was high enough that the woman, when she spilled her coffee in the drive-through lane in her car, spilled it into her lap and suffered second and third degree burns. And she sued. Now, if you think about it, you're going to give me a drink that if I put it to my lips is going to give me a second degree or third degree burn. I'm a little pissed about that. Second degree burns blister. Third degree burns remove flesh. The McDonald's, by the way, lost. And that's why all of the cups now say in giant letters, "Caution, this is hot." Because they decided that the actual temperature the coffee was coming out at was too high to be reasonably consumed. They thought the average that was demonstrated was way too high for the average they claimed. I think in the long run, it was reduced from several $100 million down to just a couple million. But still, this woman did not exactly have a happy time spilling her coffee in her lap in the drive-thru. So the only difference between doing Z versus T is whether I know the population deviation or not. Everything else gets treated exactly the same. So let me go back to confidence intervals. We did confidence intervals for mean where I knew the standard deviation of the population. We did confidence intervals where I didn't. We did confidence intervals for something else. What was the something else? We did confidence intervals for proportions. I do a survey and I find out we did one on Sarbanes-Oxley and a sample of 14 out of 200 or something like that. And we said, oh, that's 0.07778 or something like that. Percent passed. Proportions are more common than means. The largest test of proportion in the country happens tomorrow. Who do you vote for? The largest test of proportion in the country. All right, wait a minute. That means pi is the population performance proportion, and p is the sample proportion. So I need a sample statistic again, and I need a standard error. So I have to ask you two questions. First, what was the standard error formula for a proportion? Because we used that in the last section. If you go to the formulas at the end of chapter 8, that should be there. I think we used p times 1 minus p over n. We did the square root of the whole thing because it was the square root on top and the square root on bottom. That's our standard error. Guess what? A calculated statistic gets calculated the same way here as it did for a mean. You take p minus the one you expect and divide by the standard error. We will do one of these on Wednesday. Hope you all have a wonderful rest of your day. If you came in late and did not get your homework back, please come get it from me. That's how I'm taking attendance today. Also, I did post the key for the homework. If you've got questions, go take a look, then come talk to me.